Out the sound. Okay, so yeah, this is going to be a talk about basically developing abstractions for topography handling and seismic simulation, essentially to make it more straightforward to actually build these overarching applications that we care about, so things like your FWI, your RTM, all of your imaging algorithms, and a whole bunch of other sort of algorithms that we need to do seismic simulation for. So this talk is going to be in roughly 4 parts. So the first part is going to be talking about how we can actually take like topography and sort of like abstract it. The next one is going to be sort of, and also talking about like, what do I mean by abstraction, right, in a software sense. The other aspect is sort of like immersed boundary methods, so how we're actually going to implement this topography, how this is all implemented from a kind of high-level perspective, right? I'm not going to get too deep down into the workings of it. And then finally, I'm going to show some applications, like seismic modeling, seismic imaging, all that sort of stuff. Realistically, all the stuff that people are here for. Yeah, that's all at the end. So have fun with that. So yeah, we basically have a whole bunch of new hardware for Land Seismic. I need to do the thing after the same thing. So, oops. Let's minimize. There's no mouse. Hang on a second. Sorry. Does that sit off the top of everything? Okay. So yeah, we have all of this new hardware, right? We have all of these miniaturized nodes. We can deploy these sort of surveys that are far denser, with far better geometries. They have much longer offsets, all of these things, right? We can deploy them much faster and much easier. But despite all of this, our processing for land seismic is often a lot more basic than for marine seismic. So we have many fewer sort of case studies for things like FWI, RTM, all this sort of stuff, all of our kind of cutting edge algorithms. So why is that? Well, there's a couple of reasons. If you need to do simulation, which you need to do for RTM, FWI, you have all these problems, like obviously strong elastic effects. You've got your surface waves and your ground roll, so on and so forth. You have your like shallow surface heterogeneity. So basically, because you have in the shallow layers all of these, basically all sorts of different materials, it's all jumbled up. So this basically means that your source gets very chaotically scattered. You get loads of noise. You get loads of really complex reflections. Often this upper layer is very poorly consolidated, so you're also going to get attenuation. You have a high noise floor because you've got all sorts of noise going on in the background. And finally, we have the issue which this talk is mainly going to focus on, which is that of actually dealing with irregular topography, right? So obviously this causes things like very complex reflections, you get multiples, you get diffraction around the surface, and so on and so forth. So it really introduces a lot of complexities to the modeling. So why do we care, right? What happens if we just say, there's not that much topography, we'll just ignore it in our modeling? Well, it turns out it gets quite ugly quite quickly. So this here is basically showing it's basically an FWI with a couple of different sort of topographic profiles. So the middle row, so left is the true model, middle row is basically if you incorporate topography in this, and the right is if you neglect topography. You can see particularly where this topography gets really rough, it just completely destroys the inversion that we've got in, well, realistically through most of the domain here, but certainly in the sort of the area which is influenced by the boundary. So if we want to do imaging, we want to be confident in our imaging, we do almost certainly need to have a sort of be able to accurately capture surface kinematics. But the problem here, right, is that if we're doing seismic modeling, or if we're doing FWI, right, the seismic modeling isn't really the point. It's not really the whole thing. It's actually only this really sort of tiny bit of the like of our code, of our workflow, right? It's just this bit and this bit here, right? And we've got all this other stuff bolted onto it. And then even within this sort of like forward modeling and your adjoint modeling, gradient calculation, well, actually inside this propagator, we've got all sorts of other stuff going on. So we've got an update stencil, we've got source injection, receiver interpolation, we've got all your absorbing boundary conditions. You need a complex subsurface model. You're going to have like snapshotting and gradient calculations. You've probably got some sort of like compression algorithm built into that. And we're going to try and shoehorn topography handling into this. So effectively, this topography handling is like, despite being crucial to the overarching success of this algorithm, it's only a really, really, really tiny component. And actually, if you start bolting all this stuff together, the complexity is going to get completely unmanageable really very quickly, right? So implementing all of this at a really low level is probably not the way to go if we want to retain our sanity and actually be confident in the result. So what do? Well, in software development, there's precisely one trick, and that's raise the level of abstraction, right? So what do I mean here? Well, essentially what you do is you take some subproblems that you have and you package them up into a generalized function. So it's basically going to simplify the system that you've got. It's going to hide all the fine details that the users need to care about. And it sort of like generalizes whatever the process is out. So fundamentally what this means is you don't need to understand how something works. You just need to know what it does, right? So a really good example of this is like in Python, you have the list. And I think there's if you're older and you're watching, you probably got an assignment in university, which is reverse a list, right? And it was some complete nightmare thing. And in Python, we'll use reverse a list by doing :-1, and it comes out backwards. And we can do things like append and remove and add lists together, despite the fact, well, what does adding a list together mean? It doesn't really mean anything, right? But because we have this nice abstraction, it's like appending them to one another. And it turns out that actually under the hood, lists in Python are not even linked lists. They're actually arrays. So yeah, I didn't know that, and you didn't need to know that. So, but essentially by abstracting all this function, this sort of like all these fine details away, we end up with this very nice building block for building high-level functionality, which is actually comprehensible, right? And so for topography, well, if we want to do this for topography, we need to think about, well, what is topography? Not from like a physical sense, where it's like, well, it's the floor, isn't it? But from a mathematical sense, which is basically, well, we've got some arbitrary geometry, and we have some boundary conditions that get imposed on it. And this boundary is like the edge of the computational domain, right? There's nothing more beyond it. We don't bother simulating how the seismic waves propagate into the air because for the most part, they don't really. So yeah, we just have this arbitrary surface and some boundary conditions that hold on it. And yeah, this is quite vague because we have a really big parameter space for this. We have an enormous parameter space for this because we have all sorts of phenomena that we might be modeling. We're not necessarily modeling seismic waves, right? We could be modeling infrasound, we could be modeling acoustic propagation, elastic propagation, so on and so forth. We've got a whole bunch of different PDEs. You've got like all your flavors of elastic. You can make it viscoelastic. You've got about 1 million different formulations of pseudoacoustic TTI, and everyone's got their favorite, so on and so forth. We also have a bunch of different applications where you might want different boundary conditions. So, for example, if you're doing like RTM, you might want a different set of boundary conditions to FWI, so on and so forth. And you have all sorts of discretizations because there's all sorts of ways to solve the problem of finite difference. I mean, it's kind of obvious that for all of these combinations, we can't just go and like implement something by hand, right? That would be completely unfeasible and frankly a waste of someone's time. So what do? Well, we come up with something that's a bit like this, where we have some geometry, boundary conditions, discretization, and we build like a nice little algorithm in the middle that goes away and figures out what the heck the boundary implementation looks like for this. And by doing this, we're basically raising the level of abstraction, right? Because we don't really need to be messing around coming up with this boundary implementation ourselves. We've now got an algorithm that does it for us. And I will explain how we're going to do that in due course. But for the moment, the thing that we really care about is like, what actually is this thing on the right, right? Like I've said a boundary implementation method, but how are we going to implement this? And the way that we're going to do this is we're going to use something called an immersed boundary. So firstly, we can talk about finite difference methods. So basically, in certainly for imaging purposes, right, for like seismic exploration, we basically always use structured finite difference. I mean, you can use like spectral elements, spec-fam's a thing, then you have to do meshing, and you can do unstructured finite difference, but barely anyone even knows that exists. So they're not the best options. We pretty much always use structured finite difference. Then the problem with structured finite difference is that it's really hard to reconcile your regular grids with a regular geometry. So this figure on the right here basically shows, well, if you just sort of naively implement a curved surface in finite difference, this is just meant to be like a curved reflective surface. And so you can see the surface is smooth, right? But the reflection that's coming off behind it has all sorts of weird artifacts trailing it. And essentially where these come from is when we, if we discretize a curved surface onto a regular grid with finite difference, effectively what we're doing is we're turning it into steps. So we're pixelating it. And then this falls out in physics. So you get all of these diffractions off basically corners on the surface that don't actually physically exist. They just exist in your discretization. So obviously what people are probably going to think here is like, oh, you can use curvilinear grids, right? We take our grid and we squash it out of shape. So it's the same shape as the surface. So, well, we have this thing on the left here. This is called a skewing transform. This is probably the easiest curvilinear transform to do. And it's not very good. So the main thing that one of the things that we really want when we do curvilinear transformations is you want to make sure that it's like conformal. So i.e. it locally preserves all the angles. As you can see, if we started out with a regular grid, right, it's all right angles, and these are not right angles. And this is a flattening transform, which is a similar sort of idea. It's a bit better because at least it's sort of right angles at the bottom, but neither of these are good. Right, so ideally, yeah, you want like a conformal map, which looks like this, and this is horrible, right? I'm amazed that someone came up with this. So not only is this really hard to make for real topography, but you also have this issue of you kind of get this sort of like squashing of resolution in certain places and stretching in others, right, to keep it all at right angles. And then the problem that you get there is, well, I mean, if the grid space gets too big, right, we have the issue of numerical dispersion. And if the grid gets too small, then your time step is shrinking, right? So neither of these great. Also doesn't help that curvilinear PDEs on curvilinear grids look really ugly. So yeah, we don't use those basically. So what do? Well, we nick an idea from computational fluid dynamics because they already figured it out about 50 years ago. So basically they came up with this idea of an immersed boundary where they say, well, we have really horrible things to mesh. So things like porpoises and hearts and like dragonfly wings, things that move and all of this other sort of stuff. And we don't want to mesh them. So what are we going to do? Well, we're going to basically just embed them in a regular grid by using modified finite difference operators. This basically means that you can have these surfaces that are very, very complicated, and they cut between the points on a regular finite difference grid. And so you have no meshing to do, and you don't have to deal with things like curvilinear transformations, which are horrible, as we've just gone over. And so, yeah, we have a little example down at the bottom here of just doing this with seismic. And so, yeah, you can see that we can deal with very substantial, very rough topography without any real issues here. So how do these work? Well, so if you think of our interior stencil, right, we've just got this arbitrary star stencil here. So these are the points in it, by the way, each of these dots. And the dark one is like the middle of the stencil for applying it. So what happens when we get close to the boundary? Well, I said before, the boundary is the edge of the computational domain, right? There's nothing else beyond the boundary. So these points that we need up here, these don't exist. So what do? How do we get these values, right? Because we can't just leave them empty. Well, we know that we have some conditions that hold on the surface. And so what we do is we come up with some exterior values, which we can estimate using a mixture of interior and boundary information. And because in coming up with this estimate, we incorporated boundary information, right? Information about the boundary conditions and the geometry of that surface. Well, those conditions are going to hold or be enforced on that surface. It's quite useful. So you can kind of think of this as like you're coming up with a solution that's incoming, right? And it's interfering with your solution that's outgoing. So this is just a really simple example for a like 1D wave propagation on a string. So if you watch here at this point, you will see that actually the solution never deviates from 0, right? Because the ingoing wave and the outgoing wave both interfere with one another. And thus you can use this to enforce the boundary condition that, like, yeah, the function is 0 on that surface. Yeah, for those of you who've done a lot of seismic modeling, you're probably looking at this and thinking, this looks a lot like doing acoustic free surface, and that's because this is exactly what this is. So that's very nice, but then how do we do this for more complex geometries, more complex boundary conditions? Well, what we can use is we can use multi-dimensional Taylor series. So these are basically like, you know what your one-dimensional Taylor series looks like? You multiply a bunch of those together, and that's your n-dimensional Taylor series. And so we can take a bunch of points in like 2D or 3D or however many dimensions you want, and you can fit a polynomial through them all, right? And then, so how do we know where we want these points? Well, if we're on a finite difference grid, we say, well, our stencil here, so sorry, just this dark point right here is the same as the dark point in this slide. So we basically say, well, we want to apply the stencil at this point, so we're going to extend a circular support region around this point, and we're going to grab all of the grid points within this, so all of the interior values within this, and we're also going to grab the boundary constraints at some discrete points on the boundary. So they aren't drawn on here because it just makes it all too messy. But yeah, the boundary in this sense isn't really continuous because nothing is really continuous for finite difference. We basically are going to pick some suitably positioned points on the surface to encapsulate its geometry. And we can use these to fit our function. So how do we do this? Well, we have this basically like a Taylor series for a single point, right? We can express this Taylor series approximating our function at a single point as the dot product of these two vectors. So we have this one here. This A is basically like all the coefficients of the Taylor series. And this delta just contains all of the derivatives, right? And so we can approximate the function f of x as the dot product of these two, or express it as the dot product of these two vectors. And so if we have a bunch of points, right, we basically end up with a bunch of different a's. So you get like, for this one, you'd have like x1 minus x0, and you'd have like x2 minus x0, and so on and so forth. And you can stack these all up into a matrix, right? But then this delta is never going to change. It's going to be the same for all of them. So you can just have this as express this as a matrix vector multiplication. And so what we can end up doing, right, is we can form something like this. So we have all of the coefficients for our interior function values. And then for every boundary condition we have, at every boundary point, we have another block of constraints. So we end up with the number of boundary constraints we have is the same as the number of boundary points versus the number of boundary conditions. And so we basically end up with a linear system that looks like this. So we've got a matrix containing the coefficients for all of our like interior and boundary constraints. We have a vector of derivatives, and then we have a vector of interior values and boundary forcing values. And so what we can do with this is we can, well, assuming it's full rank, this left-hand side matrix, we can invert it. Well, we can find a pseudo inverse more often than not, rather than an exact inverse. And we can also do the same thing with the exterior points that we don't have. So that's basically what we have here. So we've got another vector containing all the coefficients. And we can assemble them into this thing. So this is basically, this is just a big matrix operator. You don't really have to care what goes on in here. But effectively what we have here is we have our function at the exterior points expressed as some product, right, some function of interior function values and boundary forcing values. So, and you'll notice here that this is not specific to any particular boundary condition or geometry or anything like that, right? So this is one of the things, right? We have a set of generic boundary conditions, we have an arbitrary set of boundary points, and we have no real assumption of what our underlying stencil is. So we can essentially generalize this out very easily. And so what do we do with this idea? Well, we build a software framework, right? Because you don't do this by hand. And so we effectively end up with this two-step process where we have this first section, which is basically going to figure out, okay, well, what is the immersed boundary treatment we're going to apply? And then you have a second statement section that is basically going to take that and turn it into a set of modified finite difference operators, right? So to generate the operators from that. So effectively what we're doing here is we're raising the level of abstraction, right? We're basically, it means that you just need to describe what your immersed boundary scheme has to do rather than actually having to figure out what the heck that looks like from like a numerical scheme perspective. So, and we can do this by basically taking this mathematics that I've just gone over and essentially implementing it using symbolic computation, so computer algebra. So basically, if you're not familiar with that, it's like you can basically, you have these objects that act like symbols as you write them on paper, and you can take derivatives and like substitute them and all this other stuff. But then it means that, yeah, you just need to feed in like boundary conditions, a discretization, geometry, and some stencils to modify. And basically this framework that we built will spit out the modified operators that implement the immersed boundary that you asked for. And they're fed in a format that can be fed to Devito. So Devito is basically like a domain-specific language and compiler for finite difference applications. So just as a simple example of what some Devito code looks like, this is just diffusion, right? So it basically takes this initial field and turns it into this. Right? Smears it out, it diffuses it over time. So what we've got here is we just say, well, this operator is basically encapsulated in a few fairly high-level objects. So we just have our grid, we define a finite difference grid, and we define, so u is our function, so we call it like a time function. So this is a time variant function in Devito. And then we define our equation. So we basically have this right-hand side, which is u plus dt times c times u dot Laplace. So that's basically how you would write it on paper. In a pretty much one-to-one mapping, we form an equation and we build a Devito operator. So the really neat thing is that once we have this framework, right, we have this, just this simple diffusion model, and we want to put a circular boundary in there, right? Because again, remember, we're not solving any particular equations here. This can be adapted to essentially anything, right? It's not specific to, say, wave equations. So how do we do that? Well, we just need to add a few things. So obviously we need some imports at the top. We need to set up a what's called signed distance function, or an SDF. So this is basically it's a way of expressing the geometry. So essentially a signed distance function is saying at any point, how far am I from the surface and am I inside it or outside it, right? And it's positive on the inside, negative on the outside. So that's just setting one of those up for a circle. In practice, you'd use like scikit FMM or something to generate it. And then we specify a boundary. So we basically just literally feed it a list of equations that need to hold on the surface. And again, it's going to go away and it generates the essentially modified derivative stencils for that boundary. And yeah, we can just add them into the equation by using .subs. So it's literally algebraic substitution. So all in all, we can implement this immersed boundary fairly trivially from the Python layer, which makes our lives a lot easier when we get into complicated things like wave equations. So speaking of wave equations, seismic modeling, which is probably the bit that everyone's interested in. So what can we do with it? Well, we can solve all sorts of things. We can solve second order acoustic. So this is just a 3D free surface here. We can also do rigid surfaces because, again, as I mentioned, it's generalized across boundary conditions. So it will just implement whatever boundary conditions you ask for, including ones that make no sense. But in this case, yeah, you can do like a rigid surface. So say if you are simulating how sound waves propagate in air, for example. We can also do really complicated things. You can, it's basically, because we have this abstraction, it's very separable from other aspects of seismic modeling, right? So you can start to piece things together and it all just fits together like Lego bricks rather than having this sort of big, monolithic, impenetrable block of code. It means that we do very straightforwardly do things that are quite complicated, like this. So this is from the paper that we published recently. So this is the VP migration from topography model. And yeah, you can see that you get some very, very complex reflections off the surface. We can also do first order acoustic if you want to do that. So this is basically formulating acoustic as a coupled system of first order equations. So you see on the bottom, like slices through the wave field essentially. We can also do TTI, Fletcher. Well, this is Fletcher TTI. We can do a whole bunch. You can use it to do a whole bunch of like TTI and VTI pseudoacoustic wave equations, which is good because there's a lot of them. And so having it generalized again means that you can just apply the same boundary treatment and sort of implement topography in all of them with a very with like a common API. And so yeah, this is just a demonstration of this. So at the bottom here, we have this is Fletcher TTI, and this is what's called simplified QRQP. So these are just different approximations of tilted transverse isotropy for wave propagation. And you can kind of see here, like with both of these, we get the uplift. So do you remember those the artifacts that I pointed out earlier? So you can see that on the vacuum layer one, so just the naive implementation, we have all these artifacts, and then the immersed boundary is much cleaner for both cases because this surface is now actually truly smooth. And yeah, we can even do elastic, and this is actually where having all this automation, right? So having the immersed boundary scheme automatically generated really helps you, because quite frankly, these are really ugly boundary conditions. This is only to second order. If you go to fourth order, you get even worse versions of these. And they get very verbose really quickly. If you're trying to do this by hand, you would probably make all sorts of mistakes, or at least lose the will to live. So, but yeah, you can do elastic. You can do, so this is second order elastics. This is in terms of particle displacement. So no one really uses this one because it's not super stable, but you can do it. It works. And we can also do first order elastic. So this is the one that everyone uses, but you do have to use a discretization that no one uses. So yeah, if you want to deal with complex geometries, which currently people don't really do. So yeah, how can you build this into, say, like an inversion framework or whatever, right? It's all great being able to do seismic modeling, but what we care about is seismic imaging, because that's ultimately what most people listening get paid to do. So it's just an example. What we're going to do is going to build a FWI gradient. So this is the true model here. So it's basically Marmousi with some stuff cut through, basically like a topography cut through the top of it. This is our starting model, which is much smoother. And so if we do the like an iteration of FWI, we can actually build a gradient. We can build a very good gradient. That's this thing at the top here. And if you take a Laplacian of it, it's sort of equivalent to doing like an RTM on it, sort of. But we can basically see actually, yeah, we're pulling out a lot of this like fine detailed structure. We're pulling out the fabric, a lot of the shallow reflectors. Particularly, there's this sort of like at the top of the fault block here, there's like a little, I think it's called a clip, maybe. I can't remember. It's been a long time since I did structural geology. But that gets pulled out very well. So we actually get a very, we basically can build, use this framework to build very good finite FWI gradients with pretty substantial topography. So there's about a K of topography in this, I think. So yeah, and it's pretty mountainous as well. So the other nice thing actually is having this complex surface. So this is one of the things that we found. We've also found this turns up in real data as well, is that if you actually have the surface implemented correctly, it massively improves your illumination when you do FWI or RTM. You get a much more balanced illumination, or at least that's our finding so far. So this is the same subsurface model, but the surface is flat, and we actually see that the energy is much more concentrated near the surface, whilst I think so. The working theory is that this is basically used for multiple reflections, but you get a much more balanced illumination overall, which is quite nice. So yeah, application to real world data. So the long and short is it works. So Tim from Thrust Belt Imaging sent me this recently. So this is a an RTM that he built. So a TTI RTM that he built for a using this immersed boundary framework for a land data set in, I think, Alberta somewhere. So this is actually something I want to stress is basically, so 2 years ago, Tim hadn't even done like any seismic modeling whatsoever, right? And now he has a TTI RTM that can run on real data. And this is kind of the importance of having these nice abstractions, these nice frameworks, right? Because it means that people can actually have these ideas and they can actually build them. And it also means that, I think maybe I've got a bit, yeah. It means that there are actually a couple of things that we can learn from this. So firstly, yeah, if we have this high level abstraction, we can very rapidly develop and deploy these new technologies, right? As far as I know, I don't know of anyone else who's actually used like immersed boundary topography in anger, like and actually deployed it. So that's pretty cool. The other thing is, it's actually revealed that it's not just like, oh, well, you need to have this nice topography, because as I said, this is just a small component, right? It actually means that it frees you up to figure out what all the other problems that you have are and how to deal with them. Because there's actually a lot of kind of like a lot of workflow tweaks, right, that you can make. And if you're sort of bogged down underneath the weight of your own technical debt, it's a lot harder to make those tweaks or even figure out what they're going to be. And the other thing is, yeah, like having this feedback is really good for figuring out what to add. Like this is why we figured out it does TTI, because essentially asked, it's like, well, does it? And it turns out, yeah, it does. It works. So, which is nice. So yeah, in summary, firstly, future work we actually plan to do with this. So at the moment, basically what we've demonstrated is that you can build these abstractions, they work really well, you can implement all sorts of stuff with them, and they have a lot of application for seismic modeling and building inversion frameworks and things like this. So the main thing is now to do is to turn this into something production ready. So basically doing all the refactoring, doing all the software development, all the boring stuff. Also improving the code, like performance of it, because at the moment it's research code. Source and receiver handling. So again, this is the other thing, is often when you're doing land, you've got sources and receivers that are sat on the surface or very near to it. So you need to figure out how to actually handle those properly. Also, yeah, just more powerful, more flexible API, the ability to do more stuff, essentially, because the point is, once you have this abstraction right, effectively what you're saying is you're giving people a tool to just express what they want to express. So the more powerful you make the API, the more things you can express with this framework, right? The more boundary conditions you can deal with, the more scenarios you can deal with. And so, yeah, in summary, sort of like having these nice, broad, flexible abstractions, this is a sort of like viable answer to the kind of complexities that we're seeing with land seismic imaging, certainly on the modeling front, and ensuring that they're kind of contained and kept manageable. Also, immersed boundary methods are a really good way of doing this, right? They integrate really well with the workflows that we already use, with the modeling paradigms that we already use. You know, there's a lot of research behind them, and yeah, they're effective. You can develop them for all sorts of problems. And also, yeah, if we have all of this abstraction and automation, effectively, we end up sort of like really crushing the sort of pipeline between research and production down into something drastically shorter than I think most people are used to. So yeah, I think those are the real takeaways from this work. So yeah, I think we're good for Q&A now.
Thank you very much.